I know this shouldn't irritate me, but it does. Whenever I see somebody presenting some math and they come upon somewhere in there 0 raised to the 0 power, and they like hedge their bets on what the value of that is, I find it irritating because there's only one thing it could possibly be if you properly define how exponentiation works. And I've already sort of covered this, but I kind of want to cover it in slightly more detail. Okay, so what is exponentiation? It is iterated multiplication. What is multiplication? Multiplication is iterated addition. What is addition? Iterated incrementation. What is incrementation? Iterated identification of units. Okay? So, we go... Exponentiation is a very well fleshed out thing from this. Like, we've done this same sort of thing many times by the time we get to exponentiation. It should be very, very clear how exponentiation works. There should be no ambiguity as to what the starting point for exponentiation is. Okay, so when you identify a unit, right, that's sort of outside of math, and we're looking at features and what features make you a member of this category and what features make you not a member of this category. That's what identifying a unit is. But once we've done that, iterating that is basically just counting, right? And then that gets us to numbers, and once you have that, you can take numbers and you can add them together or subtract them. And in the incrementation and the additions, both cases, you start at 0. Your starting point is 0, right? So if I have an equation like 7 plus 6 equals 13, right? Really, there is an implicit 0 over there on the addition side where the addition is occurring, right? You have nothing plus 7 plus 6. You have to start somewhere, okay? With exponentiation, so we've gone a few steps further, you have to start somewhere. With addition, it's the additive identity that you start with, right? The value that when you add it, it doesn't do anything. It doesn't change the value, right? Clearly. So by the time we're at exponentiation, it's iterated multiplication. So we need to be using the multiplicative identity as our starting point. And when you raise to the 0 power, all you're doing is you're going to the starting point of how you do the exponents, and you're stopping. No operation is done other than we've identified our starting point for exponentiation, and we just kind of stopped there. That's it, right? So you can, I've shown this before, but say we've got like 2 to the 3rd. Classically, we will refer to this as it's 2 times 2 times 2. Numerically, that's correct. There's a problem, though, because what we will say in at least English-speaking countries is that this is 2 times itself 3 times. That's not true. That's not what this is. This is 2 times itself twice. But exponentiation is iterated multiplication, so we should be multiplying 3 times. We should be multiplying 3 times. Why do we only have 2 multiplications here? Because you're fucking doing it wrong. We need another multiplication, and it needs to be by the multiplicative identity. This is your 0th power here. This times 2 is your first power. This times 2 is your second power. This times 2 is your third power. Which means 2 to the 0, or anything to the 0, is 1. Because that's just our starting point. Okay? That's where you start from. So it doesn't matter what the base is. The base has absolutely no impact on what this value is. By definition, anything to the 0 is 1. Okay? And now a negative exponent. And up to this point, pretty much it looks like things that I've already said. Right? And even a little bit further. Okay, so what does that negative mean? Well, it means we're doing the opposite of multiplying, we're dividing, right? So you get 1 divided by 2, and then that gets divided by 2, and then that gets divided by 2, right? So this is your negative first power, this is your 0 power, your starting point, this is your negative second power, and this is your negative third power. Okay. Up to this point, I've pretty much, I know I've shown this before. I kind of wanted to touch on fractional exponents. So, what does it mean to have something like 2 to the 1/2? What does that mean? Okay, well 0 is our starting point. 1 is here when we've multiplied by the 1, our initial starting point 1, by 2. Here, what this should be is, there's an L there, halfway to 1 times 2, where this is your first power and this is your 0th power, right? This half is half of this, so we should be halfway to this, which means the other half has to come from multiplying by that same value again. So, this is the square root of 2. That's why. Because whatever this number is, when you multiply it by itself, it gets us here. It has to. Right. So now we can open this up to a full proper vector space instead of just possibly it being actually numbers. Now it's actually it's vectors. Vectors work here. Logically, it makes sense. Right? As your exponents. So now you can look at, cube roots, fifth roots. Fourth roots are easy because it's going to be halfway to this halfway point, right? What number times itself gets you to this point? That'll be the fourth root. Right? And then you can, so you've got the number line that you're tinkering with. That's 0 right there. That's 1 right there. That's 2 right there. That's root 2 right there. Ish. I'm actually surprised how close that came. That looks like it's really close to correct. So now if I take this and I just grow it, it should line up, right? So if I had a proper caliper that would scale these correctly, as I grow it out to 2, it should line up. Instead of being 0, 1, root 2, it should be 0, root 2, 2. Right? I should be able to grow it that way. The 1 becomes root 2, and the root 2 becomes 2. And that's the multiplication by root 2. Similarly, if I had a half right here, and I did this, and I scaled it up correctly, it should land on 0, 1, and 2 instead of 0, 1, half, and 1. Right, so 0, 1, root 2 scaled up should give me 0, root 2, 2. Right, so what I'm doing there is I'm multiplying root 2 by root 2 to get 2. And as you can probably see, if I'm multiplying by a half, right, so let's take this 0, 1, and 2, and I multiply by a half, I end up at 1. Half of 2 is 1. So now what we can do fun things. So we can take what is 1 divided by root 2? It's going to be somewhere over here. Right, so now you can sort of graph out this space. You can get values for it and graph it. Instead of just having these very discrete points. Just by sort of understanding what the fuck is happening here. Nothing profound, nothing amazing, nothing brand new, but sort of the zero power is it's important. It's your starting point. It's always your starting point. You have to have it there. And once we've understood what this is, that's there, we can make sense of fractional powers much more easily, right? Because 2 to the 1/2 has to be halfway via multiplication, halfway between 1 and 2 to the 1st power. So via multiplication, we are halfway there. So if we do it twice, we should get here. And if it was the cube root, then if we did it 3 times, we would get here. And if it was the 4th root, we do it twice, we get here. We do it 4 times, we get here. Right. Suddenly this works. It's very easy to explain how to get these fractional powers if you note that your starting point is 1. And if your starting point is 1, then anything to the 0 power is 1 by definition. This is true. This is how it really works. And it's obvious if you think about it for half a second. I don't understand how modern mathematics is like, oh, we don't really know what 0 to the 0 is. How? How the fuck do you not know this? Are you kidding me?